Swayam Prabha. Digital India. Educated India.
Hello everyone. Let's continue with the new topic this week. We'll talk about design for stiffness and we'll see why stiffness is so important in these designs. So, very simple example, and I think this kind of bookshelves we have at our home, and what we realize that it's a fully functional. It does not create any problem, but at the same time what we also realize that aesthetically it does not look good, and obvious reason is the sagging what we see here. So, anybody who is working with this kind of systems, the furniture making, the people who are working in woodworking, I think they understand the problem. If they are very experienced one, they know, and even a small sag in the support does not look good because it can be irritating to the eyes, and anybody can see that yes, although it is not breaking, it is not failing, but aesthetically it does not give a very good impression. What we realize that if the sag is too much, then it can even slip off from the supports. So, it is not very good. So, it will also affect the performance. So, what I mentioned that if it is an experienced designer and people who are expert and who know this business well, I think they do understand. Yes, to the newcomer, maybe it's a learning and they may learn it by making more mistakes. But at the same time, I think it's important that if we can learn these things right from the beginning, we'll be less prone to making mistakes. And what we realize that we need to stiffen this structure, and there are various methods, and again what you can see that yes, you do not have to just make a very thick structure or very thick wooden plank, but you can optimize, you can stiffen it using ribs or even the ends, and you can have a very, so you can see here you can use a very thin plank itself, but you will stiffen using these kind of members. You can also see that you can use this kind of box structures. So, it is a hollow from inside and stiffened using again these ribs and members you have. So, people do understand and they make use of this knowledge, this know-how whenever they make these kind of structures. At the same time also you realize that here even putting this kind of supports at the center that can eliminate any kind of sagging or even doing partitioning. So, there are various methods, and I think this is what we are going to learn in this course, how to stiffen the structure if there is a need to make it stiff or make it robust. Another very good example, and we see very often, is the corrugated sheets, and it's everywhere. I think we can encounter while going to our offices or visiting any place, we can see it very often, and it's one of the widely used structural material to make roofing. And I think closely looking at it, what we realize that this corrugation provides a lot of bending stiffness. So, if we compare it with respect to just a plain sheet, what we realize that because of the corrugation, the bending stiffness, if we try to bend, it has increased many times, and that is the reason even without increasing the overall cost or overall weight, we can still get a very good load bearing capacity, and that is the reason it is a very frequently used to make this kind of roofing. And these days these corrugated sheets are used very widely because we have now many designs, many alternatives. Aesthetically also they are very good. So, we can make even warehouses and some architectural firms, they even design homes using these corrugated sheets. So, they are very much there, and only reason we find it and we find the wide application is the strength, the strength, and that we get mainly because of the corrugation. But we also realize that if you see the application, even the polymer sheets, it's may not call it corrugated, but yes, it's again stiffened with the ribs inside, and even the top and bottom layer you have, and inside is supported through vertical walls. Again, what we see that the bending stiffness is very high. For the packaging industry also, corrugated hardboards, we see it very often, and again these kind of materials are used very often for packaging. Even these days people are trying to make makeshift beds, furnitures, and it's mainly because of the stiffness they can provide because of that inner layers and the top and bottom layers, the way we stack them, and we can get a very good stiffness. So, these days when we receive our laptops, notebooks, even the computers, what we realize that it uses all those cardboards, and it's just not one plain sheet, but it's various layers we have, and the way it's folded, the way it's packaged, it provides very good rigidity, very good support to the object inside. So, it can be laptop or any fragile item, but even the glasswares these days can be transported very easily, safely. So, it can be wrapped around, and like these days you also see a lot of origami kind of a structure. So, folding, and by folding we try to get stiffness, rigidity, and it's a very good under impact loading also. So, it's a safe. So, we can see a lot of package design these days. So, again very good application, and it's completely based on the stiffness based design. Even the consumer products and even the beverages these days, if we go to any coffee house or any tea house, tea shops, compared to just simpler cups, what you realize that if the outer surfaces are corrugated, they are very rigid, and it can support the liquid, it can support the coffee, tea inside, and it provides of course the thermal insulation, but at the same time it also provides very good stiffness, rigidity, and you can hold it, and it does not get damaged very easily. So, we understand understand the importance of stiffness and how we design things around. But when it comes to machines, I think we can pay attention to that, and what we realize that stiffness has a big role to play. So, for instance, very simple design here, and what we see here is there is a frame here, and one object which is moving at a very high speed, or yes, it has to accelerate, decelerate. So, that is why we mention x double dot. So, this is moving. So, what we realize that if it has to accelerate or decelerate, there will be huge force provided by the actuator, by the motor. So, it will act on the moving body M, and then it will accelerate with that x double dot acceleration. So, this is the actuation force, but what we have to also understand from where we get that actuation force. So, we get that reaction force. So, this is the reaction force provided by the frame, and this is the required actuation force provided by the motor. But we realize that this reaction force, if we concentrate on this part, so this block, which we can say that is a motor and taking the load, and is supported on that block. So, this is the reaction force, and this is your actuation Fa and Fr. So, body can accelerate, but at the same time the same force is acting on the frame, and yes, frame is static, it might be moving also, but in this case it is a static. So, because of this stiffness K, frame stiffness, it will deflect. So, there will be a deflection. So, what we realize that for any machine or any machine structure, we do not want a lot of displacement, and what we realize that this K requirement is there, and it has to be high, because it has to support any moving structure, any moving body, and therefore, the stiffness of the frame should be very high. At the same time, what we also realize that if you take any kind of machine, so for instance, in this case any machine tools, if we are talking about, so if we have the mass and this is the displacement and this is the K is the stiffness of the frame supporting it. So, what we can see that it's a open structure, and that may be the principal vibration mode, how it will vibrate. And if we write the dynamic equation, what we realize again mx double dot is equal to k delta x. So, delta x is the deflection of the frame. So, that we have, and suppose if we rewrite it and write the deflection, what we say that m by k here we get times x double dot, and we can always write in terms of omega naught, which is the fundamental frequency. And what we realize that this omega naught, omega 0 or omega naught, what we can call it, is under root of k by m. And when we study about vibrations, what we realize that this frequency is very important, and usually we want to have a higher value for that, because we do not want to have our structures moving or vibrating even with the small disturbances. So, that we will talk about when we talk about dynamics, but in general whenever we are talking about vibrations and related to machines, we are talking about this principal vibration mode, and we talk about omega 0, which is a function of under root k by m. K is the stiffness, the frame stiffness which is supporting, and m is the overall mass or equivalent mass which is suspended. So, if we want to increase this value, what we want to have is, because k is at the top, so we want to have higher stiffness. What we also realize that m is equally important, so that moving mass, the suspended mass has to be lower and lower. So, we are talking about k by m, not just the stiffness, but the ratio k by m. We may call it a specific stiffness, but not just the large value of the stiffness, but is the ratio, and we want to have higher value. And what we realize that many times when we want to work with this kind of things, there are conflicting requirements, contradicting requirements. So, you want to have higher k. So, many times we tend to put a lot of material, but then we realize that the overall mass is also increasing. So, how to get higher stiffness and lower the mass, so that effectively we can get high value of omega 0. So, that is a challenge, and I think that is the thing what we will be learning in this course, in this topic, when we design things for stiffness. So, there is one example here, and in electronics industry, and where we want to have surface mount component placement we want to do, and SMT devices, SMT machines we want to use. So, we will just watch a video first, and we will see how fast it is moving. So, what we realized that after looking at this video, what we realized that it's moving at a really very high speed, and many times it's very difficult to even see what's happening. So, and it's always a start and a stop. So, pick and place operations are there, and it can be in multiple axes. It may not be just one axis, but it can be moving around, and it can move in all the three axes x, y, z. So, it will have a kind of impact motion, a lot of jerk, and if you want to go for like 30 g, 50 g kind of accelerations, so quickly gaining speed and quickly stopping and settling, so that you can precisely put the components and do the operation is a very important, and therefore, this omega 0 value, which is a function of k by m. So, a square root of k by m. So, higher k and lower m. So, this is going to be very challenging, and therefore, it is very important to understand how to design the structure or how to support the different modules in the machine, so that we can have a very high stiffness, but at the same time we don't increase the overall mass. So, we try to optimize, we try to use less material, high strength materials, materials with the high E values, but at the same time we configure it in such a way that we get a very high K, so that ultimately we can get high omega 0 and we can get a very good dynamic performance. So, we will try to learn about that, we will try to learn how to get stiffnesses, how a single member can have different stiffnesses under different kind of loading, under different kind of deformations. So, we try to learn about that. We will also talk about how the arrangements, the parallel and series arrangement, how it affects the overall stiffness of the system. At the same time, what we also realize that what is the effect of transmission ratio. So, if we place a stiffness member or a stiffening member or even a spring at a different locations from the place of actuation or place of interest, how that placement even changes and affects the overall stiffness of the system. So, we will take examples, we learn about different kind of configurations, how to achieve triangulation, how to achieve triangulation in 3D space, so that we use less material, but at the same time we get a very high stiffness. We will also learn that why the loading in axial direction is preferred than bending and torsion when it comes to achieving high stiffnesses. At the same time, when we are looking for compliance, less stiffness, and where we want to have adjustment, want to get adjustment easily in certain directions, why we go for bending and torsional loads or deformations. So, we will stop here today and we will continue from here. Thank you.